we're sort of going up a level, if you like. We're moving on up to level 3 content. And what we're looking at then, rather than just saying rates of reaction, this is what we'd call chemical kinetics or reaction kinetics. The kinetic bit, of course, means movement, doesn't it? So, it's the speed of movement. If you're going to study this sort of thing, you sometimes think, well, what's the importance of it? But it does relate very well to industry. A lot of industrial processes involve chemical reactions. And, of course, you've got to determine in industry whether a reaction is economically viable or profitable. And it's only going to be profitable if your yield of product is sufficient and made quickly enough, in terms of how much you've got to spend perhaps on, it might be providing particular conditions of temperature or a catalyst or something like that. So the rates of reaction can be really, really important. I think you were talking about pollution this morning as well. Chemistry of pollution, you've got things like the rates of formation and destruction of pollutants, because, all right, they're released, but a lot of them get broken down as well. And it's when you get that sort of imbalance where you get a build-up of pollutants that they actually become pollutants, don't they? Because there's a lot of substances produced which, are, well, we have words like biodegradable, don't we, that sort of thing, which is always a little bit of a joke. Well, my favourite or least favourite degradable substance is plastic carrier bags. The ones that claim to be degradable, well, the ones that I've got forming a nice little heap of powder in the cupboard under my stairs. I'll clean that cupboard out sometimes, having put carrier bags away, because I don't chuck them out, always there to be used, and then by the time I get back to using them, they've degraded, and all I've got is a little heap of white plastic. But yeah, it's about rate of reaction, and if you've got a rate of degradation that takes, I don't know, hundreds or thousands of years, well, that's not good, is it? So there are a lot of applications of rate. Now, first thing that we need to do really is to define reaction rate using the right sort of symbols, and to come up with a formula really that expresses reaction rate. And we're going to do it in terms of concentration. And I think we have introduced the square brackets, haven't we, for the idea of concentration. So if you are writing concentration of hydrochloric acid, for example, you can put HCl inside square brackets, and that is what it means. That is a standard chemical abbreviation. It does nicely save us writing out the word concentration. But of course, when we're writing out an equation or a formula that expresses something about rate of reaction, then that's what we're going to need to use. So if we start off, right, let's call this chemical kinetics or reaction kinetics. It doesn't really matter. But this is sort of upscaling its name from last week. It's not just rates of reaction. If we've got a reaction that we don't, I'm not going to choose a particular example at the moment, just use letters that don't represent any particular substances. So, A plus B gives AB. We're synthesizing a substance. We can express a rate of reaction in terms of the concentration change of the reactants over a period of time. So we can express this using the letters. So I'll show you what I mean. It doesn't make sense really without it written down. Average, we want average rate of reaction. Rates of reaction will change during a reaction. We'll talk about that as we go along, but it's not the same throughout. So average rate of reaction for, and if we've got this reaction where A plus B is converted into AB, all right, A and B being our products, A and B being our reactants, and AB being the product in this case, we'd have a definition. So it's defined as All right, this is sort of building from what's fairly obvious, I hope. The rate at which a reactant concentration falls between two times. So, you know, time, it doesn't matter, t equals 0 and t equals 10 minutes or 10 seconds or 10 years or 300 years or 4 minutes, 15 seconds, it doesn't matter. But it's the fall in the reactant concentration is how we would start by defining this. You will find, of course, that the rate of product formation is very closely related to this, but you have to start somewhere. So it's defined as rate at which, then I'm going to use the square brackets and do it like that. So that says reactant concentration. All right, so the rate at which it falls between two times. All right, you define those as to what's appropriate. If you've got a very rapid reaction, you might be talking in fractions of a second. If you're looking at a slower reaction like formation of rust or something like that, then you might be talking about hours, days, weeks, months. So if we were going to write it as a formula, then our rate of reaction is just going to be the change in the reactant concentration divided by the time that it takes in whatever units are appropriate to get it down to a unit of time. And for that one up there then, we could write that, well, what symbol do we use to represent change? Not an arrow, delta, yeah, the uppercase delta. Change in the concentration of A, let's say. Now, actually, because it's falling, we're going to have a minus there. All right. And that can be over our change in time, which we're going to call delta T. Yeah, it's not the same T as we had for delta T as temperature. This is one of the problems. That sometimes you have to be careful, and if you write a formula or an equation out like that, this is why we define the terms sometimes. You know, you'd say, oh, rate equals this, where A is one of the reactants and T is time in seconds or in years or in, you know, whatever you like, really. So that would be a way of expressing a rate. Okay. So it does. We've got to consider what sort of units you're going to have for your rate of reaction. So you're going to have units of concentration on the top, aren't you? So a change in the concentration of the reactant on the top. Time in sensible units, we would be talking, well, what's the SI unit for time? Seconds, yeah. So if we use SI units, which we should do, what are we going to have on the top then? What's the unit for concentration? Sorry? Moles, yeah, moles per one of them, yes? So that's on the top, divided by seconds. And so our units will actually be, how will we write that? Moles, decimeter cubed, and then what? S to the minus 1. Yes, good. All right, yeah. Yes, to the power of minus 1, S to the minus 1. So, yeah. All right, you see, your maths has not been wasted. The idea, the indices bit is actually one of the most important bits for chemistry, indices and logarithms, because, of course, they are the reverse of each other, aren't they, really? Honestly. But yes, when you've got something over something else, all right, the something else that's underneath is to a negative power, all right, it means divided by. I mean, moles per decimeter cubed is already like that, isn't it? So moles per decimeter cubed per second, that means. When you think about it, that makes sense. So the change in concentration over a period of time is a change in moles per decimeter cubed per second. Yeah, that's all right, isn't it? So far, so good. Right, I'd always have to work from my notes with these to make sure that I don't miss anything out. I'm a bit prone to losing bits. Okay, if we move on from here then, I mean, if we've got an example, it is sometimes just worth putting one in because, you know, just talking A and B doesn't really help. If we've got a reaction between hydrogen gas and iodine gas, this is one that comes up over and over again, actually. It forms hydrogen iodide, which is also a gas. We use this one, I think, in the equilibrium section as well. It's one that's just a very common example. All right, so if we take that, and obviously there are going to be factors that affect this reaction, like concentration and temperature and all that. But if we assume that it's studied at a particular temperature and the reaction is stopped at a particular point, and you can determine how much iodine there is at that particular point, how could you actually detect how much iodine there was? You could use something to show it up. Yeah, what does iodine react with? Starch. Yeah, curiously, you can use starch as an indicator in that sense. You've used iodine to test for starch, but of course, conversely, you can use starch to test for iodine. That was supposed to be the principle behind last week's practical with the tipping backwards and forwards, that it was supposed to show the iodine by putting the starch in as an indicator, but yeah, I think we over diluted and yeah, didn't get what we were supposed to get. Anyway, you could run that at a particular temperature, then stop it and work out how much iodine there is. So at a given temperature, it doesn't matter what, stop by cooling. That's you can just plunge a reaction vessel into a bucket of ice and you will pretty much stop the reaction. Swirl it around in the ice, you can stop it quite quickly. So at a given temperature, stopped by cooling, and remaining, well, because it's a gas, it's a little bit awkward, but iodine measured, let's just say, let's keep it fairly simple. If we got, well, let's say at 100 seconds, the iodine concentration, a little bit odd to think about as a gas, but all right, if we say that the iodine concentration had fallen from 0.01 moles per decimeter cubed to 0.008 moles per decimeter cubed, average rate for that then, average rate is what? Right, okay, let's sort this out. What's the change in concentration on the top? Working it through, 0.01 minus 0.008. Yeah, that's the change. And then the time on the bottom is 100. So what do we got on the top? The change is 0. You don't need a calculator for that. Yes, 0.002. I should really have put another 0 after the 1, to be honest. If you're going to use, it's not so much, is it significant figures? No, you'd say to 3 decimal places, wouldn't you? And then it's a bit easier to see, because actually, if you put another 0 after the 1, it looks like 10, take away 8, and you get the 2 a lot quicker like that. It's sort of a, a bit of a trick of the eyes almost, isn't it? And so that divided by 100, okay, that's getting quite a small number. What are we going to do with that then? Yes, that's what I made it. Yes, we need 2 more decimal places, don't we? So there's your 100 there, and then you've got your 0, 0, 2. So a bit untidy, to be honest. But units, of course, moles per decimeter cubed per second. This is where, it becomes a bit more obvious how standard form is definitely useful. So how do we write that in standard form? Right, 2.0 times 10 to the minus 5, yes. Right, okay, good. Now, you could alternatively look at the rate at which the product appears. Right, it's going to be related to this, but it's another option, and it depends what's the most easily measured aspect of your reaction. Okay. Right, how much space have I taken on there? Quite a lot. I will go on to the next one. All right. So the alternative is to look at the rate of product, well, the rate at which the product concentration rises. All right, so product concentration, all right, square brackets, rises. So we'd express that, again, it's the change in concentration of the product over time. So we'd have a similar sort of approach to this, but this time, because the product is appearing, we've got a positive. I'm just going to put it in to show we haven't missed it out, but this time, of course, it's delta AB, so the change in the concentration of AB, and again, over delta T. Now, if your reactants and products have simple ratios of 1 to 1 to 1 to 1 to 1, then that's fine. You do have to modify this, of course, if you've not got ratios of 1 to 1, as we will see. So, as long as you... Oh, let's put reactants first. It seems to be a more sensible option. So as long as that ratio, reactants to products, is 1 to 1, then what you're going to have, and it would be the same then, we didn't mention the concentration of B, but of course that's going to be in the same, that's going to be the same calculation as for A, isn't it? So what you would actually have is change in A over the change in time is the same as the change in B over the change in time, which is the same as the formation bit. Of course, the change in product concentration over the change in time. So, they're all related to each other. So hopefully that's not too scary so far. So your average rate of reaction is going to be one of those, depending on what you can measure. All right, and we've looked at some different reactions, and some things are much easier to measure than others. Yes. Now, if it's not one-to-one, then obviously, yeah, okay, we've got to think about this. You've got to think about what it means in terms of the number of molecules of substance being used to create a different number of molecules of a product, perhaps. So, I'll give you another example here. Nitrogen pentoxide decomposes into nitrogen dioxide and oxygen. And the equation for this is 2 moles or molecules of nitrogen pentoxide gas will decompose to give us 4 moles or molecules of nitrogen dioxide, nasty, and 1 of oxygen. All right, so remember, you know, an equation represents the smallest number of molecules or atoms or species, I suppose is the best word to use there, that would react with each other. But ultimately, it's expressing how many moles react with each other. It's not how many lots. That's still creeping into some people's assignments. You know, that's like saying 2 lots of nitrogen pentoxide gives 4 lots of nitrogen dioxide and 1 lot of oxygen. No, molecules or moles is what it's actually representing. Right, if we've got that reaction, for every 2 molecules of nitrogen pentoxide that decomposes, then you get 4 molecules of nitrogen dioxide produced and 1 molecule of oxygen. That's what that means. So the rate of nitrogen dioxide production is what value of the nitrogen pentoxide disappearance? That doesn't make sense, does it? If you compare the appearance of nitrogen dioxide to the disappearance of nitrogen pentoxide, which one changes more rapidly? It's the nitrogen dioxide. You're getting more particles of it. So if you're measuring, if you double through, you know, here you've got a difference of 2. But if you double it, of course, you've got a difference of 4, haven't you? And if you doubled it again, you'd have a difference of 8. And it, you know, it's because you've got more of them, you will get an increase quicker. That doesn't really make sense necessarily, but you will get more molecules of nitrogen dioxide appearing than you've got molecules of nitrogen pentoxide disappearing. So let me just write this down so it makes some sort of sense. The nitrogen dioxide is actually produced at twice the rate. Because if you're looking at change in concentration, yeah, if you double 2, you only get 4, but if you double 4, you get 8. So, you know, that has gone up. It's twice the rate, if you look at it in terms of concentration. Twice the rate that the N2O5 decomposes. All right, what about the oxygen then? The oxygen is produced at, if I was to write the same sentence but put oxygen here instead, oxygen's produced at half the rate, yeah? Oh, keep to the same. Okay. Now, you know, we're not actually talking concentrations here, but if let's say if at it doesn't matter, but a particular temperature and other certain conditions. This little thing, you have to have, you've got standard conditions and things like that, which we'll be including in some definitions as we go along. But if at a particular temperature, the rate at which N2O5 decomposes just at one particular point, and this is going to take us on to drawing curves and measuring tangents. I don't know whether you've measured tangents at all, but if it was 1 times 10 to the minus 4 moles per decimeter cubed per second, the rates of production of NO2 and O2 are all right. For the NO2 it would be, yep, all right, so yeah, so we've got 2 times 10 to the minus 4. It gets very tedious writing out the units in this, but there's worse to come. And for the oxygen it will be yeah, a half, or 0.5. Yeah. Yeah. Should we do it like that, or should it really be 5 times 10 to the minus 5? No, because it's between 0 and 1, isn't it? Yeah, sorry. Yeah, sorry. Yeah, reduce my interference there. Okay. Right, well, things are going to get significantly more complex, but the next thing we need to consider is what actually happens in experimental measurement of rates of reaction. It depends on the reaction. The ones that the marble chips and hydrochloric acid, that behaved quite nicely because you got a gradual change, but you didn't lose, you didn't lose all the marble chips during the reaction. There weren't any other changes occurring, but there are other influences that you could consider. For example, if the reaction is an exothermic one, in other words, one that releases heat and warms up the solution, right, what will happen to the rate of reaction? It'll increase, yeah. Now, that will interfere with it, won't it? So you're not actually then carrying out your reaction at a constant temperature. Similarly, of course, if it's an endothermic reaction and it cools it down, that cooling effect can, in effect, slow your reaction down. But the other thing to consider is, of course, what happens to the concentration of your reactants as the reaction goes on. Well, the concentration of your reactants will, that's what we've just written, that they will fall, won't they? Your reactants are used up. Now, concentration is one of the factors that affects rate of reaction anyway. So as you go through your reaction and your reactants start to disappear, what will happen to your rate of reaction? It will slow down. And you saw that happening. It's not actually so obvious with the solid materials, but of course you also had the hydrochloric acid was reacting as well. So the hydrochloric acid was being used up. So as your reaction between the marble chips and the hydrochloric acid continued, you were getting less and less HCl in your hydrochloric acid. It was becoming less concentrated, and if you'd left it for long enough, you'd just end up with water, wouldn't you? Because all the HCl would have been used up reacting with the marble chips to make calcium chloride. Well, I suppose it would be a calcium chloride solution, assuming that is, I'm not convinced that's soluble. I think it actually forms on the outside of the chips from the look of some of them. But obviously you lost your carbon dioxide, but water. So that water production is diluting your remaining hydrochloric acid, as well as the HCl itself being used up. So you're actually changing the concentration of your reactants as the reaction goes on. There's nothing you can do about that unless you can remove your products and you keep topping up your reactants. Well, how are you going to do that? It just doesn't happen, does it? So what you tend to get is that curve that you were seeing. If you were doing the production of the gas, you got the curves that rose fairly steeply and then started to plateau off. And if you were doing the loss of mass on the electronic balancers, you got the drop, which did start to flatten off, I think. But they will reach a point where you've reached the end because there is no more reactant left. So we have some issues to consider with this, really. But experimental measure of rates of reaction, we've got, like I say, another practical later this afternoon, in a little while. And then next week we will do a sort of simplified version of the assignment one. All right, but experimental measurement of rate, should put the full thing in, rate of reaction. So what you've got to monitor then is either the concentration of your reactants or your products. You might not be able to do that directly. You might have to be sampling your reaction mixture and perhaps titrating it with something else, or sampling it and using an indicator on it, or sampling it and, I don't know, doing something else to it. Or you might be able to see something appearing, or you might be able to collect something, or there's all sorts of aspects of this that you can measure that we discussed last week. But this is where it then becomes things like titration, the more accurate measurements, and things like light absorption, changes in colour, changes in electrical conductivity. Those were some of the ones I was mentioning last week. Those are the sort of techniques that then become really critical. And this is the sort of equipment that we haven't got a lot of. We can do titrations. That's about the limit, in terms of things like colour intensity and that sort of thing. It is a really important technique for measuring rates of reaction. Not so much colour perhaps, but absorbance of certain wavelengths of light. And it is something that you'll meet at university, but it's not something we've got the equipment for at the moment. So what you have to monitor then, you've got the options, it doesn't matter, but concentration, I could just have put square brackets on their own for that, I think. But reactants or products over time. You can't necessarily do it continuously. Sometimes you would have to do it at what we would call instantaneous points. So you'd say, right, the rate at this time, at 10 seconds it's this, at 20 seconds it's that, at 30 seconds it's that. Right, so, the changing rate is something that will then become evident, of course. So you've got titration is an option. We used to use some elaborate titration techniques that I've gone off them. So light absorption is quite an important one to put in. Colour change. It's hard to judge that by eye, There are others, I'm not going to put etc., but there are other techniques. The colour change one, I think I've told you, we do have a piece of equipment called a colorimeter that literally measures colour. And what you do with the colorimeter is you put solutions of known concentrations into it and produce a calibration curve. So you draw a graph that tells you what the known concentrations give you in terms of colour. And then you can put your samples from your reaction mixture in and read off the values on your calibration curve. But our colorimeter has sat in a drawer here since I've been here, and I'm not about to get it out. Although, I don't know, who knows? Maybe one day. So there are a lot of possibilities, but in terms of colour change, you're going to use colour change in the assignment. And I've told you it is just about the disappearance of a black spot behind some sort of pale yellow precipitate that forms. But it is a remarkably accurate procedure, I must say. Okay, what you would get then is going to be this change in the actual concentration as the reaction goes on. And you have to bear this in mind. So, this is part of what's going to explain any sort of graph that you get. And the rate is actually going to change over time. Something like change of reaction rate with time. So you would get, let's move this up so you can see it. If you were just looking at concentration, I'll just put 2 square brackets there to represent concentration, and time along here. What you would expect to happen with your reactants, you'd expect them to start high, but as they get used up, of course, as they react, their concentration will fall, and eventually you'd expect it to plateau out at 0, wouldn't you? Won't necessarily, but let's assume it's sort of pretty much there. So that's your reactants. Once they're all used up, that's that. This introduces actually an idea about equilibrium that's coming on later. A little while before we get to that. But yeah, you don't necessarily use all your reactants up. On the other hand, of course, the products, well, they're going to appear at the same rate, but inversed, if you know what I mean. They're going to rise at the same sort of rate as your reactants are used up. So here's our products. I'm putting plural for both of those for no obvious reason, but one or more reactants, one or more products. The concentration falls for the reactants while it rises for the products. If you did have an equilibrium situation, the reactants wouldn't drop to 0, the products wouldn't go quite so high. If I just divert a little bit to explain what I mean by that. If reaction reaches equilibrium, what we've got happening is equal rates in both directions of a reversible reaction, so that it appears that nothing's happening. Once it's reached a sort of stable point, what you get for that, using the same colours, but it wouldn't drop right down to 0. You'd get this point flattening out like that, and then this one coming out like that, where, all right, so it just continues forever, basically, at the same rate then. And what you have there, here you've got equilibrium, and it appears that you've got no change in concentrations. It doesn't mean the reaction has stopped. It just means that it's going the same rate both ways. So you're getting the same rate of change of products and reactants, and yeah, it looks like nothing's happening. And that is important because we will be back to the idea of equilibrium. Okay, on to this idea of tangents. Oh joy. Now I'll need to copy an example onto the board. I think that's, I don't know, I can probably draw it. We'll see. Right. Using tangents well, it's only ever going to be an estimate, so to estimate rate. Yeah, the thing with tangents is you could take a tangent, you could take the rate at any point in a reaction. Ideally, we get that initial rate, but very often we can't actually do that. But the rate after, let's just say t seconds, right, t being a number of seconds, is, well, it's the slope of a tangent drawn at that point on the curve. Okay, so what is a tangent? All right. I'll just try and draw one and see how it comes. A simple one. If I just start with a simple version, let's see. It's just not very easy to draw certain things on this board. Right. If we're looking at reactants, let's say the reactants start up here. Would it help if I use different colours? Probably not. Let's put a red line in. Let's say that the reactants change like that. All right, so that's our. And what we're measuring is the concentration of our reactant in moles per decimeter cubed, and along the bottom we're measuring time in, and we should use a slash really for before the units. Right, so concentration in moles per decimeter cubed and time in seconds. I've not really left myself enough space. If I want to measure the tangent, the instantaneous rate of reaction, let's say at, I'm going to say, just to make life easy for myself, I think, here, t seconds. I'm not sure that's going to make it easy at all. I've got to draw a tangent on that curve. Now, how much trigonometry have you done? And do you know what tangent is in trigonometry? The problem is actually drawing the thing. And I don't think Excel will do it for you. I'm not certain about that. I suspect somewhere in the depths of it you could get it to draw a tangent at particular points. But a tangent is a straight line drawn just touching the curve at that point. So we're drawing our tangent there. Our straight line has got to just touch the curve at that point. So it's got to slope in a way that represents the instantaneous slope at that point. What you have to get is a line where the angle of the curve on each side, well, between the curve and the straight line, is equal. All right. Now, the easiest way to do a tangent is actually to just do a full line so that it touches the axes, to be honest. And it's going to be a little bit tricky here. I don't know if I can do it using the drawing. I don't think I have an option to move I'm going to try and do it by hand. What I've got to do is draw a straight line that touches just here but makes an equal angle either side. So it's got to be something like this. I should have done it all in one go. Oh no, that's way out because it's actually hugging the curve up there. It's the problem with these, they are rather thick. I might just have to move the point I've drawn it at. Because what I seem to have done is drawn a tangent for here. Roughly. Not very good. So yeah, my tangent is more like that, all right, for that point. So this is now my, that's what I'm going to do actually, is just cheat. Yeah, if in doubt. I haven't done it yet. I haven't finished with it. That is giving us the slope of the curve at that point. Okay, but we've got to calculate what it is. It's this distance. Use another colour. If I use, let's say, if I call this A here and this B and this C, it's the change in concentration here. That's our change in concentration, and that is the change in time at that point. So the rate at T is the change in concentration, which is B minus A, actually, isn't it? Divided by the change in time, which is C minus A. And it is the slope of that line. So at that point, at T, the slope is represented by that tangent. It's drawing the tangent is the tricky thing. It's a bit like drawing lines of best fit. You know, you're wiggling your ruler about trying to get it on there. But the really important thing is, if I just sort of enlarge what happens in that area, let's bring that. If this is your curve, I'll try and make it a little bit more obvious. And let's say we're drawing a tangent at this point, because that's, you know, what we want to know the slope of. You need to get, your tangent has to just touch at that point. Oh, that's useless. Trouble is, by the time you started on this, it's too late. Can I enlarge it any further? Might be easier if I start with the straight line, actually. If I start with my tangent. Yeah, okay, never tried it this way before. Then I could have a curve that came in and... That's cheated a bit. It's got a flat bit on it. But this angle here needs to be the same as this angle here. All right, so that and that need to be equal. And you're taking the tangent at that point. And it's supposed to give you the instantaneous rate at that point. All right, so you've got this to look forward to. Now, yeah, you can draw it right back to the axes like that. Alternatively, you can just do a small triangle. It doesn't matter, because you know how triangles work, that if you've got the same angles, it doesn't matter how big they are. I forgot what they call them. Is it similar triangles? There is a term that describes, because the ratio between the sides will be the same no matter how big you make it. So with this one up here, we would get the same ratio if I had drawn it like that or like that. It doesn't matter. You don't have to draw it right back to the axes. You get the same tangent. And that's because of the rules of triangles. And I think this is probably the only place I ever use any form of trigonometry. So, oh, it's so clever, though. It's maths, and maths to actually get this relationship between the the sides like that. It's yeah, it's quite Yeah, interesting natural rules, if you like, aren't there? So because that's a right angled triangle, you know, you will always get that same ratio, and it doesn't matter how big you draw the triangle. So what I'm going to do is to give you an example to draw and take some tangents of. So graph paper at the ready. All right, so go and get some graph paper at the side. Somebody can be graph paper monitor while I find the question. Let's put this on pause.